Hello, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I'd do differently. Today we're going to be getting into web security with Next.js and Supabase. OWASP Top 10 Security Headers and File Uploads. Without further ado, let's get into it. So, security failures in web applications tend to follow a pattern. Something that felt safe turned out not to be. SQL queries built with string concatenation, session tokens stored as local storage, file uploads stored in the file system, environment variables with the next public prefix that accidentally exposed a secret key. Most of these aren't hard problems to prevent. They're problems that weren't thought about at the right time, at design time. Before the code was written, when fixing them is cheap. After they're in production, after data is exposed, the cost is categorically different. This video is about the specific security decisions I made building my Next.js and Supabase e-commerce platform, how each OWASP Top 10 risk applies, what the architectural mitigations are, and where the remaining attack surface sits that require active discipline. The OWASP mappings. The OWASP Top 10 is the authoritative list of the most critical web application security risks. The useful framing for this video is how many of them are structurally mitigated by my architecture versus requiring active per feature vigilance. So injection, parameterized by default, right? Supabase's query builder never concatenates user input into SQL. This is structurally prevented. Broken access control. RLS adds the auth predicate to every database query at the database layer. Server actions add the ownership check in application code. These are two independent layers. The cryptographic failures. Supabase handles session token storage, encryption at rest, and TLS. HTTP-only cookies prevent token exfiltration. Insecure design. The whole topic of this series. Security headers and CSP. These are addressed in slide 7. Security misconfiguration. Environment variable discipline. Secret management. Components with known vulnerabilities. The NPM audit in CI. Dependabot. Software and data integrity failures. Lock files committed. Supply chain risk. Logging and monitoring. Structured logging with SafeLog. Covered in the observability videos. Architecture handles most of this. The remaining surface is where discipline is required. So cross-site scripting, server components eliminate the risk. Cross-site scripting requires two conditions. User-controlled content reaches the browser, and the browser executes it as JavaScript. In the traditional single-page application path, an API returns user data. JavaScript renders it using inner HTML or dangerously set inner HTML. And if that rendering does not sanitize the content, the user scripts execute. The server component path. User's data is stored on the server into HTML. That HTML is sent to the browser as a string. This is a completely inert artifact. There is no inner HTML call. There's no client-side execution. React's JSX escapes all string interpolation by default. This always renders as text, never HTML. The escape is enforced by the JSX transform. It's not a developer convention, it's a compiler guarantee. The remaining cross-site scripting surface in a Next.js application. Dangerously set inner HTML. The name is the documentation. Use it only with explicitly sanitized content. Eval and new function. external scripts from untrusted CDNs, NPM dependencies with embedded cross-site scripting vulnerabilities. Those are the remaining cross-site scripting services in a Next.js application, just to bring it back. And content security policy in the second layer. If we have the default SRC to self, this blocks external script sources, and script SRC self without unsafe inline or unsafe eval blocks inline script execution. Frame ancestors none prevents clickjacking. CSP limits the damage of any cross-site scripting that does execute. SQL injection requires user input to be concatenated into a SQL string and executed by the database. Supabase's query builder prevents this structurally. Every method call generates parameterized SQL where user input is passed as a separate parameter, not embedded in the query string. The classic injection, where name is plus user input plus if user input is or one's is one. Yeah, the query returns all rows with Supabase.eq name and user input generates where name is assigned to one with user input as the parameter value, even if user input is drop table products. The database treats it as a literal string, not SQL. That is the classic injection. The classic injection where name is assigned to user input, and if user input is or 1 equals 1, the query returns all rows with Supabase.eq name user input generates where name is 1 with user input as the parameter value. Even if user input is drop table products, the database treats it as a literal string, not SQL. Yes, it's that important. RLS is the second layer. Even if injection were somehow possible, every query against user scope tables with auth UID equal to user ID is appended. An injection payload would need to satisfy that predicate to return useful data. When using raw SQL via Supabase RPC, always use the parameterized form. Pass user input as a function argument, not concatenated into the SQL string. Supabase's ORM methods are safe by default. We hope. Raw SQL requires discipline. CSRF. Cross-site request forgery. This tricks a user's browser into making an authenticated request to your application from a malicious site. The browser sends the session cookie along with the forged request, and the server processes it as legitimate. Server actions called via JavaScript are resistant to the classic HTML form CSRF pattern because they use content type multi-port form data or application JSON, which a cross-origin HTML form submission cannot replicate with the same header. By primary CSRF, defense is same site lax on the session cookies. This prevents the cookie from being sent on cross-origin sub-resource request. A form post from evil.com won't include the session cookie. For sensitive mutations, checkout, refunds, I validate the origin header against my known domain. A request from an unexpected origin is rejected before it reaches the mutation logic. This is a second layer, not the primary defense. So we're going to move on to file upload security. File upload is one of the highest risk features in any web application. There are 5 attack vectors, each one with a specific defense. Malicious file execution. A PHP or JavaScript file uploaded and then served from the same domain can execute in a server or browser context. The defense: store all uploads in Supabase storage, never in application file system. Serve from a separate subdomain or a CDN, not the application domain. Okay, MIME type spoofing. The content type header is set by the client and can be any value. A file named photo.jpg with a .exe magic byte signature is not an image. Okay, it is not an image. The defense: Use the file type library to read the actual magic bytes from the file content and verify the real format. Never trust content type. Okay. So malware uploads. A user uploads a file containing malware that gets served to other users. The defense: scan your uploads with ClamAV or Cloud Scanning API before making them available. Quarantine pending scan completion. SVG with embedded scripts. SVGs are XML and can contain script tags. Serving an SVG on your application domain executes its script in your origin security context. Stored cross-site scripting. Defense against this: sanitize SVGs with DOM Purify before storage or serve from a separate domain. Path traversal: a file name like here should never reach the storage layer. These are processed by a naive file storage implementation and they can write to arbitrary paths. The defense: never use user-provided file names in storage paths. Generate UUIDs for all storage keys. This user-provided file name is metadata only, not the file storage path. Security headers. Security headers SVG show 6 headers and what each one instructs the browser to do. This is 6, 1, 2, 3, 4, 5. We have 5, but all right. So strict transport security tells the browser to only connect over HTTPS for a specified period. With include subdomains and preload, it prevents any plaintext connection to your domain, even on the first visit. Content security policy, the most powerful and most complex header. This defines which sources are trusted for scripts, styles, and images and connections. A well-configured CSP blocks script injection, data exfiltration, and clickjacking. X-frame options prevents your page from being embedded in an iframe. Blocks clickjacking attacks. This is superseded by frames ancestors none in CSP, but still useful for older browsers. Okay. X content type options no sniff prevents the browser from mime sniffing responses and executing a file as a different type than declared. Referrer policy strict origin when cross origin controls how much referrer information is sent with requests. This prevents leaking URL paths containing tokens or user IDs to third-party services. Permission policy limits which browser APIs your page can access. Disabling camera, microphone, and geolocation by default reduces the attack surface if cross-site scripting occurs. These are all set in your nextconfig.js in the headers function. One configuration location applied to every response. Dependency security. Every NPM dependency in your project is a part of your attack surface. A compromised package had access to your environment variables, your file system, and the network. Real attacks have exfiltrated API keys, installed crypto miners, and corrupted data. The risk scales with the number of direct dependencies, the depth of the transitive dependency tree, and whether dependencies run at build time, test time, or in production with access to secrets. My mitigations. NP audit in CI. This fails the build on high severity SVEs. Dependabot for automated dependency update PRs. Minimal direct dependencies. Every package is a liability. A 3-line utility function is safer than a 3 megabyte package. Lock files committed and verified in CI. This prevents dependency confusion attacks. Content security policy for client-side package. A compromised client-side package is constrained by the CSP from making unauthorized network requests. The limit of these mitigations: they catch known bad packages, a malicious package that was clean at publication or one with a 0-day bypasses the NPM audit. There's no complete solution. Risk reduction is the goal. The limit of these mitigations are: they catch known bad packages, a malicious package that was clean at publication, or one with a 0-day bypasses NPM audit entirely. There's no complete solution, but there is risk reduction, and that's the goal. We're moving on to secrets management, right? What goes where? Very important. The most common secrets management mistake in Next.js is a prefix error, right? Next public Supabase URL is correct. The anon key is intentionally public. Next public Supabase service role key is a critical vulnerability. It puts your service role key in the JavaScript bundle sent to every visitor. Next public variables are included in the browser bundle at build time. No prefix means server only, available in server actions and API routes, never sent to the browser. My secrets, Next public Supabase URL and Next public Supabase anon key. These are public, intended to be visible. Supabase service role key, Stripe secret key, and TOTP secret have no prefix and live only in server action. The secrets audit. After next build, grep next static for any secret strings. If service role key or Stripe secret appear in static bundle, you have a leak. This should be part of every CI pipeline. If a secret is exposed, rotate immediately in the provider. This invalidates all existing sessions that used it. The audit logs are for unauthorized use during the exposure window. Post-mortem to understand how it actually happened and implement pre-commit hooks with secret scanning to prevent recurrence. So we're going to go to my pre-launch security checklist. 4 categories you must run before every major launch, right? Or you, I'm saying me, but whatever. Authentication. HTTP only, secure and same site lacks on session cookies, session tokens not in local storage, right? MFA available for accounts, account enumeration prevented with generic error messages, rate limiting on login and password reset. Authorization, RLS enabled on all user scope tables. Server actions verify user owns the resource before any database call. Admin routes protected in middleware. The anon key in client. Service role key, server only, right? Adversarial test suite passing and cross-user access. Unauthenticated call. Privilege escalation. All returning the correct errors. Input and output, no dangerously set inner HTML without explicit sanitization. File upload validated from Magic Bytes, please. Stored with UUID keys. No user input concatenated into SQL strings. Content security policy header configured and tested. The infrastructure, security header set up in Next config.js. HTTPS enforced with HSTS preload. Secret audit clean. Nothing in the browser bundle. NPM audit passing. Dependency lock file committed. Run this checklist before every launch and every major feature addition. Automate what you can. MPA audit in CI. Adversarial test suite in the CI. Secret scanning as a pre-commit hook. Security is architecture first. Server components eliminate the inner HTML cross-site scripting path. Server rendered HTML is not a string, not executable code. CSP is the second layer. No dangerously set inner HTML without explicit sanitization. Supabase's query builder is parameterized by default. SQL injection is structurally prevented. Okay. RLS adds the auth predicate at the database layer. 2 layers that don't require developer discipline on every feature. Same site as lags. This prevents CSRF on session cookies. Server actions called via JavaScript use a content type. HTML form submissions cannot replicate. Validate the origins header for sensitive mutations. File upload. These are stored in Supabase storage. Validate mime from Magic Bytes. UUID storage key. Scan for malware. 5 vectors. 5 specific defenses. The next public prefix puts the variable in the browser bundle. Service role key. Stripe secret key. JWT secret, no prefix. Audit your bundle before launch. Grep next static for any secret strings. For a client, security on this platform is architectural. Cross-site scripting is prevented by server components and CSP. SQL injection by parameterized queries and RLS. CSRF by same-site cookies and origin validation, file uploads, use UUID keys and MIME validation. Okay. No secret keys exist in the browser bundle. The pre-launch checklist is run before every major release. I'm Fleshed Out Thoughts, and I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're working through security architecture for your own platform, CSP configuration, file upload defense, or pre-launch checklist, please reach out. I'm open to freelance projects and consulting. The full post is linked in the description. Complete security checklist, CSP configuration, file upload implementation, and the OWASP mapping. This is the final video in the e-commerce platform series, 19 posts across API contracts, authentication, authorization, web security, state machines, database design, caching, cap theorem, rate limiting, proxies, async system design, concurrency, estimation, data management, database scaling, front-end architecture, and observability. The full series is linked in the description.